Hello everyone, welcome to another one of my Leetcode videos. In this one we'll do Leetcode 1443, which is minimum time to collect all apples in a tree. So we're basically given a tree and there are some apples on the tree, and starting from the root or the 0 node of the tree, we need to find how long will it take for us to gather all apples and come back to them. The ones marked as red are apples, so in this case we'll need to go 1, 2, 3, 4, 5, 6, 7, 8 to pick all the apples. That's basically the question. So what will be our approach to solve this question is, if I'm at a certain node 0, right, and I basically at this point need to decide, should I go to the tree below or should I not go to the tree below, right? And so how do I know if I should go to the tree below? So if there's any apples in this tree, I know that I should go, right? If there are no apples in this tree, I know that I should just not go at all and just go to the other side if, again, there are apples on this side, right? So similar logic applies here. Like if there are any apples on this side of the tree, then I should go, pick the apples and come back, right? Similar here, if there are any apples on this tree, I should go pick the apples and come back, right? So basically we'll do for each child, right? For each child subtree, if the child has apples, right, if anywhere in its subtree, then we go there, pick the apples and come back. So then that will be 2 plus the min time of the child, right? So why 2? Because we need to go to the child and come back, right? If the child does not have any apples, right, so if there are no apples, and this is if it does have apples, so if there are no apples, then it's just 0, right? So we basically sum up this property for each child recursively. So this one has no children, right? So for the very leaf nodes, our value will be 0, right? Because there is no child, so we'll end up with the minimum time of 0 because it already is on the node with the apple. If we come here at node number 1, see the child node has an apple, yes. We'll add 2 plus 0 because 2 plus min time child, and then we look at the other child. Yes, it does have an apple, so we'll have 2 plus 0, right? And then when we look at 0, then so this equation will be for this node over here, and this will get a value of 4. And then when we look at the node 0, we'll say, does this have an apple? Well, the child doesn't have an apple, but if this is greater than 0, that means the whole child subtree has an apple. 0, because if the min time is greater than 0, we know that somewhere down there's an apple, right? So since this is 4, this is going to be 2 plus the min time of this, which will be 6, right? So it will be 2 plus 4 for this node. And similar logic over here. So the min time of this node will be 0 because none of its childs have apples. So it will be 0 and 0, right? Because it will go into this case where the child doesn't have an apple at all. And so when we come here 6, we see that the child does have an apple, right? Because it's red. So it will be 2 plus the min time of the child, which is 0. So this will be 6 and 2, so we get a total of 8, and that's our answer over here. So with that, let's go ahead and solve this. So first, since we're given that the edges is in an array, right, and the form of this array is going to be AB, where A is strictly lesser than B, we need to be able to put this in a map where we can, easily look up the children of any given node. So I'm going to go ahead and create a map of integer to a list of integers, which will hold the node to the children of the node. Now we just have to loop through the edges and make sure we insert all of our edges into the map. So I've gone ahead and done that. We loop through each edge, and if the edge doesn't already exist, we initialize it with an empty list, and then we put both directions, like edge 0 to edge 1 and edge 1 to edge 2. Now the question is, why do we put both directions? So if you look here, the list is actually sorted from A to B, and the length of the list is 2, the edges. But up here, they don't actually guarantee us that the child will be greater than the parent, right? So we could have a tree that looks something like 0, 2, 3, 1. So this is a valid tree, but our edges will look like 0, 2, 0, 3, and 1, 2, right? So we can't just index one direction, because if we just index 1 to 2, we wouldn't know that 2 has a child of 1, right? So we need to index both directions, but we need to keep track of what we've visited so we don't, repeat the node. So once we visit 0 to 2 and then we come to 1, we'll see that 1 has a child of 2, but since we'll keep track of what we visited, we'll ignore children that we've already visited, so that we know that that's actually a parent. So now that we've done this, we'll just go ahead and create our recursive function, which will recurse and compute this minimum time recursively as we described earlier. So I've gone ahead and created our recursive function, which will take in the index for which this has to find the min time. It takes in the node to children, so basically the map we constructed here, the set of integers we already visited, because we want to know what we visited so we don't count it as a child, and a list of boolean describing if there's an apple at that node or not, right? So now let's go ahead and implement this function. So the first thing we want to do is obviously add the I to our visited, so that any subsequent recursive functions don't treat this I as a child, right? Next, we'll initialize our min time to 0 and then loop through all the children of I. So this creates a loop around all the children of I, and if that I doesn't have any children, because the leaf nodes, they don't have any children, we just default to a new linked list. So the first thing we want to do here is make sure that this child isn't actually a parent, or not something that we've seen before. So we'll go if visited.contains child, that means it's actually a parent, then we just continue, we skip this one, right? Otherwise, what we first do is find the min time of the child. So we have it here, the child's time is basically find min time of child and basically everything else over here. Now that we have the min time of child, we can use the algorithm that we described earlier. So is there an apple in the child's subtree is the first thing we need to know. So there will be an apple if either hasApple.getChild is true, right? So if the child itself is an apple, that means the child subtree has an apple. Or if the child time is greater than 0, that also means that there's an apple somewhere maybe further lower in the subtree, because the child time is greater than 0. If there was no apple, the child time would be 0, right? So if there is an apple in the child subtree, what we'll do is we'll add 2 plus our child time to our min time, because that means we need to go visit that child and come back. So we'll add 2 plus child time to our min time. And otherwise, if there is no apple, then we just don't do anything, because we're just not going to visit that child. So at the end, we just return our min time. So with that, let's run this code and see how it does. Oops, this was not named correctly. Another misnamed variable. Oh, I missed it here. We have to do a plus equals, because we have to add it for each child. Alright, accepted. Let's try to submit. Cool. Thank you so much for watching. I'll see you in the next video. Cheers.